Hi, in this lecture we will continue with the reactions of alkenes, synthesis and reactions. So in this particular topic we are going to cover hydration of alkenes, addition of water by oxymercuration. Before addition of water by oxymercuration, let's review what is a hydration reaction. A hydration reaction is a reaction in which a water molecule adds itself to an alkene in the presence of a strong catalyst like phosphoric acid. In industry, ethanol is synthesized from ethylene and water with the help of phosphoric acid catalyst at a higher temperature at 250 Celsius. So let's look at this reaction, how the reaction occurs. Let's draw the reaction mechanism. First, let's draw the alkene. As you remember from the previous parts, alkene, the pi electrons will act as nucleophile, and here, since we are using acid catalyst we can show as hydronium ion, because water plus acid we can show as hydronium ion. In the first step, let's show with different color. In the first step, alkene, ethylene, will act as a nucleophile, and electrons will flow from nucleophile to electrophile, which is hydronium ion. This hydrogen is electropositive. Then we are going to break this hydrogen-oxygen bond, and we are showing with curved arrows. So as a product, we are going to generate a carbocation, a positively charged carbon species. Here, since this alkene is symmetric, you can add this hydrogen on this carbon or on that carbon, it doesn't matter. But as you remember, if the alkene is not symmetric, so we have to follow the Markovnikov rule, which I'm going to state a little bit later. So then we are going to generate water, and this is the first step. These are the intermediates. In the second step, water is going to act as a nucleophile now, and carbocation will be electrophile. Water will be added to positively charged carbon, and we are going to generate our addition product. Here I'm going to draw it. I will write all hydrogens here, and I'm going to write with a different color the things that we added. Basically, here we have a hydrogen, and here we have OH and H. Still, here there is a positive charge on oxygen, because there is a 3 bond around oxygen. In the next step, there is going to be a third step. In the third step, a surrounding water molecule is going to pick up one of the hydrogen from this positively charged oxygen, and we are going to end up with the neutral alcohol. Don't forget, in this type of reactions, we generally produce neutral alcohols. Here, let's draw here the alcohol OH. I'm not going to draw detailedly now. Plus H3O. Again, I'm not drawing like this. So this is the catalyst. As you see, we regenerated the catalyst and we form our addition product, which is alcohol. If you look at this specific example, 2-methylpropene, if you look at the carbon-carbon double bond, the substituent on carbons are different, and it's an asymmetric alkene. When we have an asymmetric alkene, follow the Markovnikov rule. What does Markovnikov say? He says, or the rule says, that when we are forming carbocation, hydrogen will be added to carbon with fewer substituents. So here I have zero substituent, because these are hydrogens, these are not substituent, and these are methyl substituent. So this carbon has two substituent, this carbon has zero substituent, so hydrogen will be added to carbon with fewer substituent. Again, as you remember, I made this joke. I set up by myself another rule, Dr. Ibrahim's rule. I'm changing this Markovnikov statement. What is my rule? My rule says that hydrogen will be added to carbon with more hydrogen. It's easier to remember. Don't worry about the substituent. And then OH will be added to carbon with less hydrogen. So you can basically remember this rule. Okay, so after learning what is a hydration reaction, we are going to learn another method to hydrate alkenes. This method is called Oxymercuration demercuration procedure. In laboratories, using of high temperature strong acid catalyst way is difficult. It's not environmentally friendly, and also it's not easy to control. So instead of that, we use another method for hydration of alkenes. We call it oxymercuration demercuration. What's the reaction? Basically, you will have an alkene, and alkene will be hydrated in the presence of a mercury reagent. What is the mercury reagent? We call the mercury acetate. Mercury, OAC, is acetate, and then the procedure is two-step. In the first step, mercury adds itself to carbon-carbon double bond, and it forms a cyclic mercurinium ion. In the second step, water adds to this intermediate, and we introduce an OH bond here, and this cyclic structure breaks up. And in the last step, when we use sodium borohydrate, mercury carbon bond breaks, and we introduce a carbon hydrogen bond. So basically, this is a Markovnikov product. What does it mean? Hydrogen is added to carbon with more hydrogen. Sorry, Dr. Ibrahim's rule. Here you see, and OH is added to carbon with less hydrogen. So there is zero hydrogen here. Here there is one hydrogen on the carbon-carbon double bond carbons, and we are adding hydrogen to carbon with more hydrogen. So basically, the oxymercuration demercuration generates an alcohol from an alkene. It's a hydration reaction. We add water, and it's Markovnikov product. You don't have to worry about the mechanism. It's a little bit complicated, but at the end, when you have an alkene, when you have a mercury acetate plus this reagent, if you just see mercury acetate, most probably the reaction will be oxymercuration demercuration. Just add water to alkene in Markovnikov fashion. Okay, let's look at here. What products would you expect from oxymercuration demercuration of the following alkenes? Again, Markovnikov. Let's write here. So there is here one hydrogen, right, on this carbon. Here two hydrogen. Hydrogen will be added to carbon with more hydrogen. So this will be CH3, and the OH will be introduced here. So instead of writing this way, I will write a skeletal structure. It has 1, 2, 3, 4, 5 carbon. So let's draw 5 carbon chain for 5. 1, 2, 3, 4, 5, and there will be no more double bond here. And hydrogen will be here. I'm not showing hydrogens in skeletal structures. OH will be added to this carbon. Let's look at this one again. What is the longest chain? 1, 2, 3, 4, 5. Let's do the same. 1, 2, 3, 4. 1, 2, 3, 4, 5. Double bond here between 2 and 3. So this has 0 hydrogen, and this one has 1 hydrogen. So hydrogen will be added here, and OH has to be added here. There was already a methyl group here on the second one. So this is the product. Let's move to different hydration procedures. The next topic is hydration of alkenes, addition of water by hydroboration. let's assume this hypothetical situation. In the laboratory, you are working in a laboratory and you are asked to synthesize an alcohol from an alkene, and you have here an alkene, 2-methyl-2-pentene, and you are asked to synthesize 2-methyl-3-pentanol. Let's look at is it like, can we synthesize by oxymercuration, demercuration process, or acid catalyzed water addition? Let's look at here. This carbon has 0 hydrogen and this carbon has 1 hydrogen. These double bond carbons. If we follow Markovnikov addition, hydrogen will be added to carbon, more hydrogen, so it will be added here. Let's write H, and OH will be added here. And if you look at, this is the other way around. So we have to start from this reagent and we have to synthesize this one, but if we use oxymercuration, demercuration, we cannot do this one. OH will be here, H will be here, but your supervisor or your boss is expecting you to synthesize this one from this one. How can we do it? There is a way to synthesize it. The procedure is called hydroboration. What is hydroboration? When you have an alkene and when you have this reagent, which we call it BH3 or boron trihydride. You know boron from periodic table 3A. Let's write here BHH. It's one of the exception to octet. It has only 6 electrons around, so it's highly electrophilic for that reason. So when you react an alkene with boron trihydrate, what happens? Boron trihydrate add itself to the carbon-carbon double bond in a fashion that BH3 splits into BH2 and H. Hydrogen is added to one carbon of the double bond and BH2 is added to other carbon. Then when you use a second step, because it is two-step procedure, in the second step, if you use hydrogen peroxide in basic conditions, OH minus is base, what happens? Carbon-boron bonds breaks and we introduce OH here. So it's an oxidation reaction, or hydrogen peroxide is an oxidizing reagent. So at the end, if you look at here, hydrogen add itself to carbon with fewer hydrogen, which is non-Markovnikov product. BH2 add itself to carbon with more hydrogen, but later BH2 carbon-boron bond is broken and OH is inserted here. As a result, we get a non-Markovnikov product. Second, if you have cyclic alkenes, what happens? We also have a stereochemistry selection, or stereoselective. The reaction is stereoselective. What does it mean? Hydrogen and BH2 is added from the same side of cycloalkene, or from top phase or from bottom phase. So if you look at here, when we add BH3 to 1-methylcyclopentene, we synthesize as an intermediate an organoborane intermediate. When boron, BH2 and H is added, we call this is an organoborane or organic borane intermediate. If you look at hydrogen and BH2, they are dash dash, meaning that they are away from the plane. And what's going to happen later? If you use hydrogen peroxide, BH2 will be replaced by OH. At the end, OH and H is added to the same side of the ring. Like you can say this is away from the ring, or this is coming out of the ring plane. So at the end we have a certain stereochemistry and we say sign addition. Sign addition means to same phase or same side addition. Why this happens? Why we get non-Markovnikov product? Why we get sign addition product? I'm going to explain in this slide. When we have 1-methylcyclopentene and when BH3 is added to the carbon-carbon double bond, it adds in this fashion, in this way. at the same time, like boron hydrogen bonds break and boron carbon bonds form, carbon carbon double bonds break, and hydrogen carbon bonds form. This is a step which all bond breaking and bond formation process occurs simultaneously. So what does it mean? In order for BH2 and H added at the same time, they should, like, it should approach from bottom or from top, and BH2 and H can be added only from the same side, from bottom side or from top side, because the bond formation and bond breaking processes all occur simultaneously. So there is no way that this hydrogen can be added to the upper side and BH2 can be added to the lower side or lower phase. There is no possibility for that. For that reason, BH2 and H is added in from the same side, and we say this is sign addition or same side addition. That's the first thing. Second thing, when alkene is not symmetric, for example, here we have hydrogen and CH2, here we have methyl and CH2, right? So this is not a symmetric alkene. For BH3 to be able to approach here, BH2 could be added to carbon with fewer substituent, meaning that BH2 is a bigger group sterically, CH3 is a bigger group sterically, so BH2 cannot be added to this carbon. Why? Because there is a methyl group and this carbon is sterically crowded, so it will not be easy for BH2 to be added to this part, but hydrogen can be added here and BH2 can be added to carbon with like more open space or with sterically less crowded place. That's the reason why we get Markovnikov. What is Markovnikov? Non-Markovnikov. What is Markovnikov? Markovnikov says that hydrogen will be added here and the other thing will be added here, right? Non-Markovnikov says that hydrogen will be added to the other one, not here. So why it's added there? Because sterically it's more open. As a result, hydroboration reaction produces first non-Markovnikov product, second OH and H has to be added to the same side. So for example, we don't get cis, we only get trans for this particular case, but you don't worry about cis or trans. The only thing you have to worry about, OH and H has to be added to the same side. Sometimes it happens, the product will be cis or sometimes maybe trans, but the important thing, OH and H has to be on the same side. I'm going to show you some animation to show you what's happening basically. So let's go to first one. Okay, I'm going to show you BH3 addition to ethylene. So look at here. These are two separate molecules. They are close enough to each other, and we are going to form first an organoborane intermediate. Okay, let's start. See, BH3 is approaching to carbon-carbon double bond. Carbon-boron bond is forming. Boron-hydrogen bond is breaking. Hydrogen-carbon bond is forming. Carbon-carbon-pi bond, double bond is breaking. This is the transition state. You can see that. As you see, it's broken. The pi bond, sigma bond is forming. And BH2 and H is added to the same side. So that's the reason why we have sign addition or same side addition, BH2 and H. Later, another reaction or second step, hydrogen peroxide plus OH minus is going to change this BH2 into OH. That's the reason why OH and H will be on the same side. I'm going to show another animation. It is this 1 methyl cyclopentene. So let's say again we have BH3 and the alkene. We are going to see how it is happening. So see, like boron hydrogen bond is breaking, hydrogen carbon bond is forming, this double bond is almost broken, and this carbon boron bond formed. As you see, they are, yes, here. So H and BH2 added to same side. So I'm just going to show you the symbols. This is BH2, this is H. So, okay. Let's move to some exercises. We will solve two exercises, or we will do two exercises. Let's look at the first one. Show the structures of the products you would obtain by hydroboration oxidation of the following alkenes. Let's look at again what are the rules for hydroboration oxidation. If you see BH3 in the first step, in the second step, it's here basically, hydrogen peroxide and a base hydroxide, let's say. What you will end up with an alcohol, non-Markovnikov product, and sign addition of H and OH. So I'm going to here draw this product. So how many carbon we have? 1, 2, 3, 4, 5. Let's do 5. 1, 2, 3, 4, 5. There is a double bond between 2 and 3. So what's going to happen? So this is 1 hydrogen carbon, this is 0 hydrogen, right? It's non-Markovnikov, so hydrogen will be added to here now, and OH will be added here. So you don't have to show H and OH is added to the same side. Why? Because we have an open chain. This is an open, it's not a cyclic alkene, so these bonds can rotate. So whatever you get, it will go to its lowest energy conformer. So we don't show stereochemistry when we have open chain alkenes. Let's look at here, this one. Again, here we have 1 hydrogen, here we have 0 hydrogen, hydrogen non-Markovnikov, hydrogen will be added here, OH will be added here. So the product will be this. I'm drawing skeletal structure. So hydrogen here, we don't show hydrogen, OH here, right? Okay, so this exercise is a better exercise because it's a cyclic alkene. You have to show stereochemistry. Okay, so let's draw this one. It's hydroboration oxidation reaction, right? Okay, so we are going to add water to double bond. It's non-Markovnikov. So let's look at here. There is 1 hydrogen. So hydrogen will be added here now because there is 0 hydrogen here, non-Markovnikov. So this is not OH, it's 0 hydrogen, 1 hydrogen. Okay, hydrogen will be added here and OH will be added here. So let's say this is CH3, right? And this is OH. Okay, this is partially correct answer. Why? Because I have to because since this is a cycloalkene, we have to show the stereochemistry of the product, right? OH and hydrogen, I will show it you here, should be on the same side, dash dash or wedge wedge. So let's do this way. I'm going to show OH wedge, and I'm going to show hydrogen, because hydrogen and OH we added, so they have to be on the same side. They have to be wedge wedge. And what is the next one? CH3 has to be dash. Okay, or if you want to draw another way, it's going to be this. Instead of like wedge wedge, just say hydrogen dash OH dash, and what's going to happen? So let me just erase some part. This one, okay. So HOH is added to the same side, right? Dash dash. There was a methyl here. Let me draw this. It's CH3 is here. Okay, either you draw this one or that one, it's going to be correct. So we finished chapter 8. These are the study problems for you, and this is the reading assignment. Thank you so much for watching this lecture video.